ago, it attracted a lot of attention from the environmentalists when it was recognized that all of the fossil fuels that possess nitrogen in their structure are combusted with oxygen and form a family of nitrogen oxides. NO, the monoxide, N2O, N2O3, etc. These are all viewed as toxic pollutant gases that are emitted into the atmosphere from smokestacks, automobile exhaust, cigarette smoke, anything combustible with nitrogen. And they go up in the atmosphere and interact with the ozone layer to deplete ozone. Why is that important? There's a big ozone hole over the Antarctic, and that permits the ultraviolet light to penetrate the Earth and cause global warming, because the ozone is the filter for that ultraviolet spectrum. So the environmentalists became very concerned about nitrogen oxides. And then we came along in 1977, 78 to say, my gosh, it is an important molecule in the body because this is how nitroglycerin works. This is how nitroprusside works. A lot of important cardiovascular drugs are prodrugs that convert in the body to nitric oxide, and that's how they work. Also, it regulates a lot of biological processes. Our first publication was in 1977, showing that it activated guanylate cyclase to make cyclic GMP to cause relaxation of smooth muscle, airway smooth muscle, GI smooth muscle, subsequently vascular smooth muscle. Today, there are 120,000 publications in nitric oxide research. It's become one of the most popular areas in all of medical research. Most big multinational pharmaceutical companies have projects related to nitric oxide. There are 60 or 70 at least, or more perhaps, biotech companies around the world dealing with some aspect of nitric oxide biology, all trying to develop important products and drugs in this field. On the right-hand side is a partial list of some of the biological effects. The first effects were relaxation of smooth muscle, airway, GI, and vascular smooth muscle. Then came inhibition of platelet aggregation. It participates in cytotoxicity of parasites, cancer cells, all sorts of things. It's got numerous effects. No way that I could summarize this for you with all these publications that are out there, but I'll give you an overview and a flavor towards the end of the talk. When cyclic GMP was first discovered in urine of rabbits in 1963, a few labs, including mine and 3 or 4 others, became interested in cyclic G as another potential intracellular second messenger. We said, my goodness, maybe here's another one besides cyclic AMP. And we started looking at the enzymes that participated in its production, its inactivation, and perhaps its effects. And we know today that there are a family of enzymes that make cyclic GMP. They're called guanylyl cyclases. They're made from 7 different genes. There's a soluble isoform that is a heterodimer, alpha, beta subunits. The beta has a heme prosthetic group with a ferrous iron, which is the target for nitric oxide. The soluble guanylate cyclase is the receptor for nitric oxide. The particulate isoforms, there are about 6, GCA, B, and C, and a couple of others that are thought to be orphan receptor cyclases. But the particulate cyclases, to date, the few that we've studied, are receptors for various peptide hormones, the atriopeptins, AMP, BMP, CMP, E. coli, heat-stable enterotoxin, guanylin, the GI hormone. They have interesting biological effects and a lot of potential for drug discovery and development. The guanylate cyclase has a lot of homology with admilate cyclase, which makes cyclic AMP. The catalytic domains are almost identical. If you mutate one amino acid, you can convert a G cyclase to an A cyclase and vice versa. So I think in evolution, it was probably a single cyclase that did both, made cyclic A and cyclic G. The only explanation I can think of. And with evolution, they diverged. The cyclic GMP, as with cyclic AMP, can be inactivated by a family of enzymes called cyclic nucleotide phosphodiesterases. There are 11 members of this isoform family, 11 different gene products. Some selectively hydrolyze cyclic AMP, some selectively hydrolyze cyclic GMP, some hydrolyze both. They cleave the phosphodiester bond to make the corresponding monophosphate, GMP or AMP. The isoform that you all know about, probably unknowingly, is the type 5 phosphodiesterase, which is the target for Viagra. Sildenafil inhibits that enzyme, permitting cyclic GMP levels in the blood vessels of the corpus cavernosum of the penis to accumulate more cyclic GMP under the influence of nitric oxide released from the nerves, which are nitrinergic nerves, releasing NO as their neurotransmitter. And as you make more cyclic GMP, the blood vessels dilate more and more, they fill with blood, and that's the mechanism of penile erection. That's why Viagra works. There are other products out there as well today. Most of the intracellular messengers, cyclic A, G, calcium diacylglycerol, regulate the activity of a protein kinase. These are often serine-threonine protein kinases that transfer the terminal gamma phosphate of ATP to the protein substrate, and there are dozens of these protein substrates. And when these proteins are phosphorylated, if they're enzymes, their activity can go up or go down. If they're structural proteins, their function can change. They can participate in muscle contraction, they can participate in motility of cells and organisms. There are hundreds of these protein kinases. There are some protein kinases that phosphorylate tyrosine residues. These tyrosine kinases are not regulated by intracellular messengers, but are tightly coupled with cytokine and growth factor receptors. So the concept of cell communication and regulation is simple. A ligand or first messenger regulates the production of a messenger, intracellular messenger, which regulates a protein kinase to phosphorylate various proteins in different compartments of the cell to produce a biologic effect. The problem is, with all of these isoforms, it can take you a lifetime to figure out who's in bed with who's talking to who. And once you figure that all out, it's a wonderful opportunity to develop selective therapeutic agents, which is what I do. I'm a clinical pharmacologist, and I do a lot of biochemistry and genetics, molecular biology, to understand these pathways so I can discover novel drugs for important medical diseases. That's what I do. So once you understand the pathways, it becomes a rather easy assignment, frankly, to go screen libraries and find interesting compounds. When we first decided to start working with guanylate cyclase to make cyclic GMP, we were quite surprised that when we made homogenates of liver and heart and other tissues, that there was enzyme activity in the high-speed supernatant fraction as well as the high-speed particulate fraction. Unlike adenoid cyclase, which was all in the particulate fraction. Guanylate cyclase appeared to be in both compartments. Furthermore, the kinetic properties of the activities were quite different. The particulate activity was cooperative with regard to GTP as substrate. Double reciprocal plots were curvilinear, implying cooperativity with multiple GTP binding sites. The soluble activity had the typical Michaelis-Menten kinetics, linear double reciprocal plots. And we thought, my goodness, we're dealing with isoforms in the soluble and particulate compartment. There are going to be different pools of enzyme, different pools of cyclic GMP, perhaps with different functions, and maybe regulated independently of each other by different hormones and drugs. Well, all of that turned out to be true, but we were sort of sticking our necks out and wishing an awful lot. And the problem was that hormones didn't activate our enzyme in cell-free preparations. One of our goals was to figure out how hormones worked to make cyclic GMP, and by understanding the coupling mechanisms and pathways, perhaps we could come up with drugs to treat various endocrine diseases where the cyclic GMP production was increased or diminished. We could come in with activators or inhibitors to treat endocrinopathies. We couldn't do it because the hormones didn't work. Because you're working with crude systems, you can't rely upon kinetic data. There's potential for a lot of artifacts. We knew that our preparations had nucleotidases and phosphatases competing for the substrate GTP. We knew that they had phosphodiesterase hydrolyzing the product that we were measuring in our reactions. So we wondered if our kinetic data were true or not. To prove that we had different isoforms, we had to purify, clone, sequence, and re-examine, and we did. It took us about 8 years to do that. It was not an easy assignment. Burned up a lot of postdocs along the way to get there, but finally we did that. But initially, I took a shortcut and said, let's add a variety of reagents to our incubations that would be nucleotidase inhibitors, phosphatase inhibitors, phosphodiesterase inhibitors, and re-examine the kinetic properties. Let's see if we could change the apparent cooperative behavior of the particulate enzyme. So we added pyrophosphate, fluoride, azide, hydroxylamine, sodium nitrite, methylxanthines, a variety of things. And quite accidentally found that some of the molecules activated the enzyme. Azide, hydroxylamine, and sodium nitrite, those three substances activated soluble guanylate cyclase. And having worked with adenylate cyclase in the activation by fluoride, which turned out to be very important and led many of us, and Gilman and Rodbell included, to discover G proteins, I thought that with the activation by these small molecules, it would help us understand the regulation of guanylate cyclase and perhaps someday to reconstitute a hormone effect in a cell-free system, which was our goal. When we put these substances on various tissues and cell cultures, we could increase cyclic GMP levels, so they became replacements or surrogates, if you would, of the hormones that were not working. And we could begin to examine function, lipolysis, glycogenolysis, etc. The azide effect was specific. It would activate some tissues but not others. It required oxygen. There was a time lag of a couple of minutes before the reaction became maximal. All of this suggested that these small molecule activators were not the proximal activator of the enzyme, but they were being converted to something else in our incubations. So we had another factor or activator. And it became quite a mystery story for a couple of years to figure out what that might be. Fortunately, one of the tissue preparations that we began working with, because of my bias and hypothesis, was tracheal smooth muscle. I wanted a clean, smooth muscle preparation without all the contamination that blood vessels provide with endothelial cells and neuronal cells and fibroblasts and everything else. We made a tracheal smooth muscle prep that was highly smooth, clean and smooth muscle. When we put azide on those smooth muscles, cyclic GMP levels went up, as it did in other tissues. And I expected the tissue to contract because I thought cyclic GMP would antagonize the effects of cyclic AMP. The effect was the opposite. It caused relaxation. What a big surprise. We did the pharmacology, dose-response curves, time courses, and within a few months, we were convinced that one of the functions of cyclic GMP was smooth muscle relaxation. Not only airway smooth muscle, but gastrointestinal smooth muscle, and then later vascular smooth muscle. I remembered as an intern and resident, I would take care of patients in the intensive care unit with heart attacks by giving them nitroprusside or nitroglycerin to lower blood pressure, decrease afterload, as we say, to rest the heart, so the heart would heal after an infarct. So I suggested to the fellows that we try nitroglycerin and nitroprusside. They caused relaxation, as was known in the literature. Nitroglycerin had been around, I told you, for 100 years as a vasorelactant. The big surprise was they all activated guanylate cyclase and increased cyclic GMP levels, which was associated with relaxation. So we now had a long growing list of compounds for which I coined the term nitrovasodilators that were nitrogen-containing substances. They were nitros, nitrosos, azidos, hydrazines. They were all, I thought, donors or prodrugs to make the reactive species of the activator. Because azide failed to activate preparations of heart muscle extracts, there was an inhibitor in heart, hemoglobin, that we purified, and it blocked the effect of all these nitrovasodilators. We went to the literature and discovered from some old literature that hemoglobin had a very high affinity for nitric oxide. And we said, my goodness, that's a potential candidate for our activator. So one night in early December 1976, my Japanese fellow Shoji Katsuki had been released from the hospital having passed a kidney stone, came to the laboratory the night before he was flying back to Osaka to help me do that experiment. And we made nitric oxide in the fume hood by mixing sodium nitrite, sulfuric acid, and ferrous sulfate, a classic chemistry reaction. We vented the gas into our cyclase incubations, and it activated all of our cyclase incubations. Eureka! We discovered that nitric oxide, a free radical, and a gas could activate an enzyme. The activation of an enzyme by a free radical had never, ever been seen before. I was quite excited about it, thought about all the potential chemistry this would now take us to. Would there be other enzymes regulated by free radicals? I thought about it. We've never found that, but we thought about it. And that is summarized for you in this slide. This is a slide, most of the students probably don't know what a Leroy set is, but I drew this slide with a Leroy set at my desk in 1976. So all the printing here is mine. My postdocs have, of course, redone it on the computer, so it looks cleaner. But nitric oxide was the intermediate of all these nitrovasodilators. And it activated the soluble isoform of guanylate cyclase. And we know today from our work and the work in many other laboratories that it does this by binding to the ferrous iron on the heme prosthetic group on beta subunit of histidine 105. And when it binds to the heme lifts off the enzyme, removing the inhibition